DARPA's Automated Rapid Certification of Software program, or ARCOS in short, is intended to research and develop methods that will streamline the assessment of software assurance evidence that will allow certifiers to quickly ascertain whether the system's risk is manageable. This demonstration aims to showcase a complete end-to-end workflow that integrates various research tools created by one performer from each of the 3 different technical areas of the ARCOS program, namely, the Design for Certification Methodology or DesCert developed by SRI and its collaborators for Technical Area 1, the Rapid Assurance Curation Kit or RAC developed by GE for the Technical Area 2, and the Consistent Logical Automated Reasoning for Integrated System Software Assurance or CLARISSA developed by Honeywell and its collaborators for Technical Area 3. Central to this integrated demo is the Evidential Tool Bus, ETB2, which has the capability to orchestrate tool executions in a distributed fashion, based on formally defined workflows. While the comprehensive details of each of the blocks in this figure is elaborated in the reports and related publications, at a high level the top part of figure shows the overview of DesCert methodology. DesCert is a formal, property-driven approach that integrates evidence generation from various formal methods-based tools used at various stages of the software life cycle. Namely, it integrates results from tools such as Text-to-Test and Clear IDE for requirements capture, analysis, and test generation, the SALI tool for model checking models and properties drawn from those requirements, Radler tool for architecture definition and system builds, the PVS Theorem Prover tool to verify claims about the Radler semantics, and the Checker Framework tool for pluggable type checking of Java code components. All the evidence generated from these tools are systematically organized based on an assurance ontology that has also been defined as a part of the DesCert approach. Whenever evidence artifacts are newly generated or updated in any of the DesCert tool chain, the ETB2 workflow is defined to identify and orchestrate the subsequent tool executions as well as initiate the organization of the artifacts based on the assurance ontology. Then it initiates automatic ingestion of the data into the TA2's RAC knowledge base and subsequently trigger updates to the TA3's CLARISSA's assurance case tool that uses these artifacts as factual evidence to support assurance claims. This demo illustrates one of the operational concepts workflow defined in ETB2 for ARCOS. The figure shows a high-level overview of the various steps involved in this workflow. In essence, ETB2 facilitates communication among different tools and services through a distributed tool bus, utilizing defined data log rules. These rules serve as formal descriptions of information flows and outline the execution order for various processes and tool invocations. As shown in the figure, following the initial establishment of ETB with data log rules, the DesCert approach begins with system modeling, which is predominantly a manual activity. Whenever there is a new artifact or a modification made to any of the system modeling components, such as when system designers check in files within version-controlled repositories, the ETB workflow is configured to detect these changes. This subsequently triggers associated downstream analyses and tools dependent on the newly created or altered artifacts. This includes formal methods-based analyses of architecture, requirements, and ONTIC type code analysis, each of which generates corresponding evidence artifacts. Similarly, when new or altered evidence artifacts emerge from these analyses, the ETB2 workflow initiates the subsequent security analysis as illustrated. Upon completion of all these analyses and the generation of artifacts, ETB2 triggers a task for creating an ingestion package, that systematically organizes all the evidence artifacts per the defined ontology and packages it appropriately for curation. Once ETB2 detects the completion of the ingestion package creation, it automatically initiates the rack ingestion step, where the evidence data is curated within the rack repository. After ETB detects the completion of the ingestion process, it instantiates the CLARISSA assurance case tool and automatically adds or updates the newly curated data from rack onto the corresponding node in the claim tree of the assurance case. Throughout these steps, ETB initiates the next tool or process execution only if any upstream tool or process modifies the information relevant to that step. Now, let's run this workflow and watch the process in action. We are now going to play a live screen recording of the ETB2 workflow execution. As the demo proceeds, the active step in the workflow will be animated on the block diagram on the top of the screen. The left side of the screen will show the console screen and the outputs of the workflow execution. On the right side, snippets of the artifacts and datalog rules used for this workflow demo will be displayed. As shown, the datalog is a formal description of the activity or tool execution shown in black bold text, along with precise details of the inputs and outputs mentioned in blue and orange text respectively as its parameters. For example, the system modeling is an activity, which is manually done, so it doesn't have any tool-related inputs, but produces outputs such as properties and various specifications that are then used as inputs in downstream tool execution such as text-to-text requirements analysis. Initially, the ETB is instantiated and set up with the tool information and datalog rules for the workflow. The console window on the left will now show the progress of the log in ETB as it is configured with information about each tool. The respective tool wrapper code and the workflow relevant processes are added one after the other. This is a one-time initial setup, and after this, the workflow execution will be fully automatic. The first process in the workflow is the system modeling. As mentioned earlier, the system modeling is a manual activity typically performed by system engineers, and they create several output artifacts. One of them is the functional requirement specification in clear notation, shown in the right side of the screen. These are functional, contingency requirements specified for an autonomous unmanned air vehicle when its battery level is detected to be insufficient to continue its course. The other output of the system modeling is property specification, which again, defined using clear notation, captures the desired safety and security properties that needs to be verified for this system by the downstream tool suite. Along the same lines, the other artifact that is defined as a part of this modeling is the system architectural specification. As shown on the screen, in DesCert the specification is captured using the rattle notation. Further, other artifacts such as ONTIC code analysis properties that are manually specified using clear notation, currently shown on the screen, are also outputs of the system modeling activity. When all or any of these outputs are newly defined or altered by the system engineers and checked in into version-controlled repositories, the ETB detects it and triggers the step in the workflow, which is tool execution. For instance, per the workflow, when ONTIC properties or the source code is newly added or changed, the checker framework tool is instantiated by ETB and the tool is executed. When the checker framework tool execution is complete, ETB initiates the wrapper process that will automatically capture the property execution results in clear notation as per the assurance ontology definition. The wrapper processes the raw tool output and identifies the precise decision outcome such as satisfied or not satisfied so that the outcome can be automatically ingested into RAC in the subsequent steps. Next in the workflow is the verification of the properties about the architectural specification using the tool called Radler. Once the Radler execution is complete, similar to the checker framework analysis results, the ETB initiates the wrapper process to automatically capture the property execution results as well as the decision outcome in clear notation as per the assurance ontology definition as shown in the screen. When ETB detects the completion of architectural analysis, it automatically triggers the execution of the next tool in the workflow, which is text-to-test. The text-to-test is a novel verification tool that uses public domain SMT solvers to automatically perform a formal analysis of functional requirements to ensure satisfaction of generic properties such as consistency, completeness, and timing dependencies. Text-to-test also performs various static analysis of the defined security specifications to ensure that it possesses defined properties as well as it conforms to the semantics of its respective ontology definition. Once all the analysis is complete, similar to the other analysis, the raw tool output is parsed by the wrapper so that meta information such as the date and time of the analysis, the traceability to the requirements, the raw output file path, and the decision outcome are captured. Similar to all the other analyses, ETB next initiates security analysis, which is also performed by text-to-test, to formally check if the specified security properties are met by the architectural specifications as well as capture the results in clear notation. When ETB detects the completion of all these analyses, it initiates the ingestion package creation process. In this step, the analysis results that were all captured in clear notation is automatically parsed by text-to-test and comma-separated files are created in a very specific format that is acceptable by RAC for ingestion. In this step, in addition to the CSV files which contain metadata of all the analysis, the actual analysis results files produced by the individual analysis are also packaged into a compressed file format. When ETB detects the creation of compressed file, it triggers the wrapper for RAC to start ingestion of all this data into the repository. Prior to actual ingestion into the repository, RAC performs various sanity checks on the data files such as conformance to data formats, correctness and completeness of all the relationships between data per the ontology,